Okay, so today we're just gonna do a little bit more practice with recursive functions. So I'd like you guys to, if you're watching the video, pause it for a second and see if you can write the first three terms of this recursive function. And then you're going to see if you can create a recursion formula to represent this sequence of numbers. So if you're watching the video, pause it. For us, we've already taken our time to do this, so we'll just take it up. Can someone tell me how they figured out the first three terms here? What do we do? That was very loud. Okay, so I already know the first term. So where do I go from there?
Do you put f in as 3? Like in the...
Well, I have to have something, I have to have f at 1 somewhere in here to plug that into. Joey, what do we do?
You have to like change fn to like f2 equals to f2 minus 1 plus 5.
Great. So when we sub in n2 for n, we're saying that's the term number, right? So this notation is a little bit different. It's like f at 1 means term 1. So n being the term number and f at 1 meaning the term's value. So if you want, you can always replace these things with tn and tn minus 1. But you should be able to just kind of follow the same trend that we do with the tn and tn minus 1 kind of idea. And Joey, what did you do from here?
I changed the f1 to 3.
Great. So we're plugging in 3 for f at 1 because it tells us that in the question. And then I have f at 2 equal to 11. Okay? And then same kind of idea with f at 3. This is the last one I need to find. I'm plugging in 3 for all my n's, so we end up with f at 3 minus 1 plus 5, which actually simplifies to f at 2. So because we actually just calculated f at 2 down here, I can actually plug that in for my f at 2 above. So I'm going to substitute f at 2 with its value of 11. Okay, so we'll get 22 plus 5, giving us 27 for term 3. So our first three terms are 3, 11, and then 27. Okay, questions for this one? Not there? No. That's weird. 220? Anyone know where Mr. Bean's class is right now?
I think like Mr.
I
Soren's
talked to
class,
Mr.
right?
Bean.
Oh.
Mr. Johnson was leaving and I talked into this.
And what did he, where did he say the papers were? Sorry, let me just pause this. All right. Recursion formula. So what did you guys notice is the main pattern of this sequence here? Bonnie?
Multiply the last term by -10.
Okay, so we times by -10 to get future terms in the sequence. Did you end up figuring out the recursive formula?
F at n equals -10 f n minus 1.
Okay, so we can write it like this, like that you use function notation, or you can write it with your tn's. So what this is telling us in plain English is to get the next term in the sequence, we take the term before it and we multiply it by -10. And that will give us, whoops, too far back here. That will give us future terms as we go along. Okay? So either of these notations are acceptable. Great. All right, so I just want to do, we're going to really quickly just do a couple extra examples with creating recursive functions, just because that can be maybe a little bit challenging sometimes. So I just want to do a bit more practice with this, and then we're going to look at something else. Questions for this one before we move forward? We're good? Okay. All right, so here's the question. I want to create a recursion formula for the sequence 2, 5, 10, 17, 26, and so on. So we're going to take a second here. We'll see if we can find the main pattern that's happening, and then see if we can work from there. So take a couple seconds, pause the video if you're watching. All right, how do we do? Anyone recognize what's happening here? Alexandra?
It's going by an odd number, so first it's 3, then 5, then 7, then 1.
Great. So we're actually adding odd numbers, or AKA odding. We're adding sets of odd numbers here. So there's a couple ways that I explained to you guys yesterday that you are... Hi. All right. Okay, so yesterday I explained to you guys that there's a couple ways that you can express odd numbers in terms of the term number. So I can express an even number. So we know all even numbers are multiples of 2. Odd numbers are 1 before or 1 after an even number. So it can be like 2n, 2n minus 1. It could even be like 2n plus 3, 2n minus 3. 5, 7, 9, and so on, right? So it's either 1 before or 1 after an even number. It could be 3 before or 3 after an even number, and so on. So the question is which one of these fits, right? So you can just guess and check here. So suppose I say my next term in the sequence is equal to the term before it plus the odd valued 2n plus 1. We will do a check for this to make sure that it actually works. So we're just testing adding a variety of odd numbers here and seeing what works. So to get term 2, I'd be taking term 1 and adding 2 plus 2 plus 1, or 2 times 2 plus 1. So I'm taking term 1 and adding 5. Is that correct? Well, I think I took term 1 here and I added 3 to it, so I don't think that's correct, right? So this actually does not work. So option 1 is a no, right? And it's totally okay to try something and it not work, and then we try again, right? So maybe we go to our next one. Maybe we'll try the 2n minus 1. Because we were pretty close here with 4, so if we had changed that to minus 1, then I think we would have gotten to 3. So why don't we try tn equals tn minus 1, and we'll add the odd number in the form 2n minus 1 this time. And then we'll do a little check for that. So we want to check it to make sure it works in technically all of these, so just be mindful that just because it works for one doesn't mean it works for all. But here we'd be saying take term 1 and add 4 minus 1, which is 3. Is that correct? Did we take term 1 and add 3 to it to get the next term?
Yeah.
Yes, we did. So this works. So when you're checking, I would probably just double check all of them to be safe. SA, can you take out your headphone, please? But once you kind of get a couple that are working, you're usually pretty safe. But you can't just check one of them, is what I'm saying. So here, I would be taking term 2 and adding 6 minus 1, so adding 5. Is that what we did to term 2? To get term 3? That is, right? We took 5 and we added 5 to it, and we got our term 3. So here, we did 5 plus 5 and got 10 for term 3. So that one works as well. And then we'll just check as we kind of go along here. But I think we can kind of see that our pattern is working. So I think we'll land on this one as our correct one. Okay, so the check, making sure that this works for each part of your sequence is important. Marianne? T3 minus 1. Yeah. So I'm just plugging it into this n minus 1 thing here. So he did know where they were.
Actually, it turned out they were in the office.
Oh, okay. Thank you for going on that hunt for me.
Bravo. So wait, hold on.
Here's your
What's
time.
the schedule for our blocks that happen in the chapter?
It's the same.
It's the same.
Yeah, so this one's just going to end at 11:35 as usual. Yeah. Okay, questions on this?
It's been a good recording.
Yeah, it's going to be lots of things happening in this recording. Sorry, YouTube watchers. All right, so we are going to try another one. We're going to create a recursion formula for the sequence 2, 10, 37, 101. So if you're watching the video, we're going to take a couple seconds, pause, and see what you can figure out for this one.
So you want us to do?
All right, so let's start with at least just the pattern of additions here. What are the additions to get to the next terms?
8, 27.
Okay, 8, 27, and 64. These are some interesting numbers here. These are actually from, oh, thank you. Always need somebody to remind me of that. So these are actually from a certain set of numbers that we learned earlier this, well, maybe we didn't explicitly learn about this set of numbers, but is there anything that 8, 27, and 64 have in common?
They can all be divided by 3.
8 cannot be divided by 3. What?
They're all numbers.
They're all numbers, yep, okay. Let's keep going. Kylie's?
8 squared is 64.
Okay, 8 squared is 64, true. 27, how does that fit? How would we even continue this sequence? I think we don't even know how to get the next term there, right? 27 squared. Alex? Ah.
Radicals.
So 8 can actually be expressed as a cube, right? So these are all cubes. I said we looked at this set earlier, but I remembered that we actually looked at the set of squares. But 8 is actually 2 cubed. What's 27?
3 cubed.
3 cubed. And 64?
4 cubed.
So can you guys tell me the next term in the sequence?
5 cubed.
Isn't it 125?
So we will add 125. So what does that give us as our next term? We're adding it, yeah.
Oh, yeah.
So what do we get?
226.
226 is our next term in the sequence. Okay, that's the first step, right? We need to know how to continue our sequence. So how do I now use this idea of cubes to express this as a recursive function? Pardon? Because we're taking 101 and we're adding 5 cubed, so we're adding 125 to it.
Should we put a cube before?
Can you go?
I feel like we should put the cube somewhere around here.
So it's going to be something dealing with Tn minus 1.
Yeah.
And
Are
then
we
n to the n cubed?
And put brackets around
n
it.
to the n cubed
No, just n cubed.
plus n cubed? Yeah, you're right.
Oh my
Perfect.
gosh.
So we're taking the term number and we're cubing it and we're actually adding it to our previous term. So we can do a little check here. This should work for any gap of terms here that I want to check. So let's say I check term 3. My formula is telling me take term 2 and add the term number cubed. So is that working for us? If I take term 2, which is 10, and I add 3 cubed, does that give me my term 3? So it gives me 37. Is that the value of term 3?
No.
Yeah.
Yes.
Yes, it is. Okay, why don't we check another one? We'll check 37 to 101. So that is, I'm finding term 4, and my formula tells me take term 3 and add the term number you're trying to find. So 4 cubed. So does this give me the next term in the sequence? Does it give me term 4? Yes, it does. It gives me 101. So that's good. So I think our formula is working well here, right? I should be able to check any term in here, and this formula should work. As soon as it doesn't work for one term, it's not right. Okay? So be mindful. Just because it works for one, you should be checking more than one for sure.
2?
At least 2. But I would, if I were you, I would just check all of them and make sure it works for all of them. I mean, there's only one other check that we'd have to do, which is 2 to 10.
Exhausting.
Okay, so these ones are different because there's no one way that we can find the answer. The patterns are different, right? So we need to kind of recognize some different patterns that we see. So that's the big thing here. My suggestion would be the very first thing that I usually do in a recursive sequence, if I'm trying to create a formula from it, is I see what's the addition to go from one term to the next. And then, for instance, yesterday we noticed that we were adding 5, adding 15, adding 45, which are all multiples of 3 from one another. So I know that there must be something to do with the multiple of 3. And then you kind of unpack it from there and see if you can try different things and see if it works. okay? If you notice that it's like, I don't know, adding 4 and then adding 9 and then adding 16, those are squares, right? So look for squares, look for cubes, look for odd numbers, look for even numbers. If you're adding 2, 4, 6, 8, 10, 12, and so on, you might be adding an even number. So like 2n, 2n plus 2, 2n minus 2, 2n plus 4, 2n minus 4, and all of that kind of stuff, okay? So we're going to move into something different now, so I'm just going to stop the video.